Hey guys, welcome back to another video on the topic of units. And if you have watched the last couple of videos, you were introduced to unit-based semantic segmentation on this mitochondria dataset that you see on the screen. And in the last video, we actually used watershed to separate any objects that were touching to get accurate object analysis done, right? So this is in a way we performed instant segmentation via semantic segmentation. Now, to measure objects, if you only take small patches of images and you segment them and try to measure these objects, then you're not going to get full information about your objects, right? Especially if your objects are much larger than your patch sizes. That's why it's very important to work on patch sizes that are larger than your objects, or much larger, at least 4 times larger than your objects, so you can catch at least some objects that are not cut off. Now, even in this example, you can see some of these are actually cut off at the edges, and you don't get the full picture. And this is a full screen image. And if you only look at these patches itself, right, most of these objects are touching the edges, and I may get some accurate measurements from these, but most of these I'll end up with inaccurate measurements if that's what I'm going for. So the best way to actually do these is by actually combining these together, the predictions together, so you can actually get like the right object analysis done. So you get the right parameters, what is the shape distribution, size distribution of your objects. Okay, after all of that, let's actually jump in. And in this video, I'm going to show you 2 things. First of all, how not to do it, because I see this mistake made in the code I went through, like on GitHub or even some of the YouTube videos. People do these 2 mistakes quite often. I'll talk about that in a minute. And I'll show you a couple of ways to actually divide your images into patches, apply this, put them together, and perform some object analysis. If that's of interest, please stay tuned for the next, hopefully 20 minutes or so. Okay, let's jump into the code right now. Okay, so I'm using my Spider IDE, and again, I'll try not to repeat what I have done in the last couple of tutorials. I really want you to go back. Otherwise, it's a disservice for people who are following these series. And then if I repeat the entire thing over and over and make these videos very long, then they actually need to be, yeah? So, but I will cover the core concepts. So what we have done in the first video when we did this unit was actually train a unit and save a trained model. And we trained it on patches of 256 by 256. These are grayscale images, so we divided a large, in fact, I divided a large data set into small patches and then trained the unit on this size patches. Now the question is, my image that I want to segment is 768 by 1024. It could be much larger if you're working with whole slide imaging in bioimages, for example. These are humongous, right? I mean, you cannot just train your network on these large images. You have to train them on smaller patches, whatever the logical patch size was. Now, so in our example, we trained it on 256 by 256 size images. These are grayscale images. My model expects 3 inputs, height, width, and number of channels, right? In this case, number of channels is only 1. So I'm going to import my model. I already have it in a separate file called simple unit model. Again, nothing to see there. As it says, it's very simple. There is an encoder, there is a decoder part, and that's pretty much it. I'm going to share those files, so don't worry about it. And everything else is pretty straightforward. We are going to normalize our data, our inputs, and OpenCV for reading images, and Pillow if we want to resize image. We'll see that in a minute, and Matplotlib for plotting. Okay, so far so good. Now, let's go ahead and import our model and corresponding weights. Okay, so I'm going to get the model and then define my model equals to get the model, right? So now my model is defined. Well, simple. I should have run these lines first, obviously. Import the libraries, not just talk about it. Now go ahead and run these lines. Now you should see the summary of my model, and if I scroll all the way to the top, you should see that my input is 256 by 256 by 1, and let's do this. Okay, 256 by 256 by 1, and then 16 filters right there, or 16 filtered images, 16 filtered images. Again, these are all convolutional layers and dropouts and so on. Okay, so this gives you a nice idea of exactly what I was doing, going all the way down to 16 by 16 by 256 and then upscaling it back, right? This is your classic unit, and concatenating in the middle. between these connections. That's pretty much it. So no tricks over there. So not much to talk about here. Now let's go back. So we know that our input is 256 by 256, and let's load the corresponding weights. I trained the model and we saved the weights as HDF5. We have used Keras. And there you go. And let's go ahead and load our large image. Yeah, like I mentioned, my large image is of the size 768 by 1024. This is the image I'd like to segment using this model. So if I just go ahead and do my pre-processing, right? I mean, what did we do for pre-processing? First of all, we expanded the dimensions by 1, and also we normalized the values. So if you look up here, my array is of size 768 by 1024 by 1. Okay, this is what we have done for training. So I'm doing exactly the same for prediction. And now let's go ahead and expand the dimensions one more time. So now we have 4 dimensions. This is 1 by 768 by 1024 by 1, right? So this is standard. I'm not doing any tricks so far. Now let's go ahead and predict. Model.predict. And in this case, I'm actually predicting it. And output, because it's softmax, the output is going to be probabilities in this case, okay, or even sigmoid. The output of this network, of this prediction, is going to be a probability. I'd like to convert that into semantic segmentation, and because this is a binary case, I'm taking everything above 0.5 probability as true, everything below as false, right? That's exactly what I'm doing, and I'm converting that into a unsigned integer 8. That's what this line is doing. So let's go ahead and predict this, and we should see an error right away down here saying that, hey, the input needs to be 256 by 256 by 1, but you gave me 768 by 1024 by 1, so I'm not gonna do anything here. This is a good thing. It's throwing us an error. But what I have seen online that people kind of, this is the mistake I'm talking about. What they do is, instead of 256, let's actually, let me comment this out and uncomment this part. You know that you can input a model by not giving the dimensions, right? You don't have to give width and height. And we do this in transfer learning when we want to get the structure of VGG16 so we can train it ourselves. But don't do the mistake of importing it this way and using a pre-trained weights to do inference or to do your segmentation. And you'll see why in a second. So let's go ahead and remove everything that we have done until now, and run these lines again all the way up to here. And if you look at the model now, it should say none, none, and channel 1. So now it actually takes in those values based on my inputs. So if I go all the way, sorry about this, if I go all the way, you see none, 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 and 1. That means it will let me run this instead of throwing an error. So if I actually load the weights, it's loading the weights, okay? And if I read the image, it should get this. And let's run all of these lines, and prediction should happen, even though my image is not of the same size, because we redid this network, okay? And if you go ahead and plot it, you'll immediately realize how crappy the results are. Sorry for my for my swearing over there, but you see how my results look pretty horrible. That's because I'm applying weights from a network that has actually been trained on 256 by 256 size images onto a completely different size image here. Even though technically it's allowing you to do this, this will yield horrible results, so don't do this, okay? Lesson number 1, do not, for training, this is fine. You get this model, now you train on larger images and then apply the model onto your larger images, that's fine. But make sure that your image that you're trying to segment and images it got trained are of similar dimensions. Otherwise, it kind of learns based on features at certain pixel size, and now you're applying it at a different pixel size. So this doesn't work. I mean, logically that doesn't work. You see the result over there. Now, the other mistake that people do, okay, let's go back to our original, right? If I go back to this and if I run, it should not run because it says, okay, hey, you have 256 by 256 and the shape is different. I've seen people change this image size, resize it. So what if I resize this from 768, by 1024 to 256, right? So let's go ahead and do that. So that's what these lines actually do. So I'm using Pillow library because it makes it easy to resize. So there, now I'm reading the same image and I'm changing this to 256, and of course it should work. Let's run this entire code one more time so you can see what happens. It should work. You should see some result, which is a crappy result. So now it actually resized my large image into a smaller image, 256 by 256, and trying to segment it. And you see the result is not good. So the lesson here is you learn two ways that you should not be doing your handling your large images when it comes to semantic image segmentation, right? Even for instance segmentation. Now let's actually see the right way. The right way is to divide this into patches. So if you know how to do that, fine, go ahead, right? If you don't know that, I'll share the code again. This is very simple. Let's remove everything. Well, let's keep the images, but let's remove all variables and start from scratch. Okay. So let's go ahead and import. And again, there is no libraries like these are all standard libraries that I'm actually, in fact, I'm not even using this, and I'm not even using these as tracking the flow of it. Okay, let me keep this simple. So here, all the libraries you should be familiar with. And the first line is basically my file that I have with my model in it, right? So the simple unit model and OpenCV, NumPy, and everything. Let's define a patch size of 256 because the plan here is to take our large image and divide that into patches of 256, predict on these patches, and then stitch them back together. That's pretty much it. And let's go ahead and get our model again by defining our width and height as 256. And now let's go ahead and write a function for prediction. You can just do this, any way you want. But in this case, I'm just going through two for loops. Okay. First of all, let's go through line by line and try to make sense. I'm creating an empty, not an empty, but a NumPy array of the same shape as my original input image, but with all zeros. And this is where I'm going to replace zeros with whatever value after segmentation. Okay. So at least I have a placeholder. And I'm keeping track of my patch number, like, okay, how many patches, and so I can kind of print them out as it's going along. Now for I in range 0 to image shape 0, which means let's go from, let's say my image is 768 by 1024, right? So from 0 to 768 in steps of 256, do something. And 0 to 1024 in steps of 256, do something. What is that do something? Okay. First of all, extract a single patch. My single patch is basically 0 to 0 plus patch size, right? What is my patch size? 256. So go from 0 to 256, 0 to 256. And the next iteration, it'll go from 256 to 512 and then 256 to 512, right? Or 0 to 0 and 256 to 512. So it just keeps going through my entire NumPy array piece by piece. And then I'm doing exactly the same thing I have done before. We have to expand the dimensions and normalize the data. Exactly the same. I'm not changing much of anything. So here we did, let me undo my image resize. But yeah, we read the large image and then we are expanding dimensions normalize and we are expanding the dimensions and prediction, right? That's exactly what we are doing. Expanding the dimensions normalize and expanding the dimensions normalize there, and we are getting a single patch shape because we are using that shape later on down here. That's pretty much it. Otherwise, nothing else going on over there. And then I'm doing model.predict on my single patch, and also doing above 0.5. I already explained that, right? This is exactly this line that we're talking about. And after that patch is done, after that single patch is done, I'm going to replace the segmented image. Remember, we have all zeros in segmented image. So replace all the pixels where I have zeros with the values that I'm actually getting from the prediction. That's pretty much it. And then move on until we are done with everything. And basically at the end of it, return the segmented image. That's pretty much it. So let's remove everything and let's run these lines. So far, nothing should happen. We just defined the function. Now let's go down and get the model, right? We did exactly the same thing before. Let's go ahead and get the model. And now let's go ahead and again, this model should be pretty much same as what we have done before, 256 by 256 by 1, and so on all the way. So pretty much the same model, and we are importing the same weights. Okay, so let's import the same weights right here. It should be fine. And the next thing is read the large image, right? We read the large image, and my segmented image is basically run this function prediction on using my model, right? That's my input and image and patch size. Okay, so let's go ahead and run this, and there you go. So patch number total, I have 12 patches. If you think about this, 768 divided by 256 is 3. 1024 divided by 256 is 4. So I have 3 by 4 patches, which is 12. So the math works out. That's a good sanity check. And you can see where it's starting at 0, 0, 0 to 256, 0, 512, and 0, 768. And then it moves on to 256 and then 512. So everything is fine now, right? So that's pretty much it. Now, where are we? So we are done with our segmented image. We just need to go ahead and have a quick look at it. First of all, let's look at the histogram. I mean, this is a quick way of checking, okay, how does my values look like? So the backgrounds are all 0, and mitochondria, they all have value of 1. So good check right there. And you can save the result. Let's go ahead and save it. I'm going to call this segment.jpg or segm.jpg. And you're visual like me. If you are visual like me, you want to have a look at it. Look at this output compared to what we had before when we did this in the wrong ways, right? These are all the wrong ways, and here is the right way. So your image and the segmented. And there are some issues like a little bit of thing. I mean, we'll clean that up in a minute actually. But overall, you can see how nice this is. You have these mitochondria. It could have done a better job down here. It's a matter of training our data. I mean, our model in a better way. But I see these two mitochondria are close by, and we can separate this. Now, I mean, at least I hope you're with me until now. And this part, I'm not going to go through line by line. This is exactly what we did in the last video, where we actually did some image processing operations, like performing distance transformation, and then segmenting the images, and defining the sure background and foregrounds, and defining the unknown region between the background and foreground, so Watershed can actually find this region between these two and then fill it, right? So this is where we're converting our semantic segmentation into instance. So please watch the video exactly before this one. Okay, so let's go ahead and run these lines up to here, where it's performing all of these operations, and it should be pretty fast. And now let's look at this output of this, our instance segmentation result. There you go. So there's our input, here is the output, right? I mean, this mitochondria is half right there. Maybe you can try patch sizes of smaller sizes, let's say, or larger sizes, but that could be better. But other than that, everything else seems to be pretty good. These two are separated right here. This one is nice, and that one is nice. I'm overall pretty happy with the result right here, as you can see. And once this is done, let's go ahead and calculate our object properties. Again, I'm using measure.regionProps table. And once you measure those, and remove the very large or very small regions if you want, then go ahead and print out what do we get. So this 1, 2, 3, 4, 5 mitochondria here, and each mitochondria with average equivalent diameter. You can report more. I mean, I'm just reporting like literally 1, 2, 3, 4 of these, but you can report many parameters. Look at the documentation for region props. Okay. Now, if you don't know how to deal with this nested for loops, if you're just getting started with Python, but you're dangerous enough to kind of play with unit, okay? And this is for you guys. There is a library called Patchify, okay? Go ahead and pip install Patchify. And as the name suggests, it takes care of patching and unpatching. So it patches the images, it unpatches. In between, you can do whatever you want with those patches. And let's walk through this code one more time. Let's remove everything from here. And I installed this, and you should not have any issue installing this Patchify. And let's go ahead and import all the libraries, and you see I'm from Patchify, I'm importing Patchify and Unpatchify, right? So I want to create patches, I want to unpatch them, okay, meaning putting them together. This part is pretty much the same as from the last section, the one that we just finished. We are getting the model exactly the same. We are loading the same weights that we saved, and I'm loading the same image here. And instead of me writing a for loop to take care of this, all I'm doing is, hey, my patches equals to Patchify, my large image, at a size of 256 by 256, and change the step size to 256. This is what I like about Patchify. It's very easy for me to change the step size. So I can change it to 128 and see how, when I put them together, how does the output look like. I can change this to 64 and see how it looks like. We'll do that in a second. So when I do this Patchify, and if you look up here, it says 3 by 4 by 256 by 256, right? This is exactly right. 768 by 256 is 3, right? And 4, so there are 12 of these total. Now I still need to write my for loop to go through each one of these patch and apply this. So all it's doing is just separating patches, so I don't have to write my own segmented image with zeros and then fill these with zeros. That's what you're saving here. And I believe Patchify also works on 3-dimensional images, so I'll let you explore that. Okay, so now I'm starting with, okay, my predicted patches is my empty list right there, which I'll populate in a minute. Same thing, go for I in range. For example, my 3 images or 3 patches by 4 patches. First of all, just to show you, 3 patches by 4 patches, this should be 0, 0, 0, 1, 0, 2. This is very similar to the last one. I'm just showing you an existing library, that's it. And the rest of the stuff is exactly the same, okay? My single patch, in this case, my single patch was something I defined, I to I plus patch size, because I was playing with the NumPy arrays. Here, it's pretty much the same thing. My single patch is my patches, ij, right? 0, 0, 0, 1, 0, 2, and so on with all of these. And then the rest of the story is the same. Expand dimensions, go ahead and model.predict. And at the end of this, to my predict patches, append the result. That's it. Okay, so I hope this makes sense. Where are we? So let's go ahead and run these lines. And at the end of this, what we should see is if you look at predict patches up here, it's a list of 12, right? It's a list of 12. We have 12 patches. Let's convert that to NumPy array and reshape it. That's what we are going to do next. So my predict patches is NumPy array right there. So you can see I have 12 patches, each 256 by 256. This is my result. Let's reshape to 3 by 4. So that's what we are doing here, numpy.reshape. And you should see 3 by 4 by 256 by 256, my predicted patches reshaped. So now I have my reshaped patches in the same order as my original patches. So now I can unpatchify. So that's the next step, okay? Unpatchify my predicted patches to what shape? To the same shape as my large image, okay? Which is 768 by 1024. So when we do that, it should unpatchify it. Reconstructed image is 768 by 1024. So we're back. Again, go through this video, these steps a couple of times. It's very simple, straightforward. Look for this code on GitHub. Go ahead and practice it. And now let's go ahead and show the reconstructed image just for sanity check. Okay, there you go. And we can also save this. Let's go ahead and save this again with the same name, segmented.jpg. I'm using the same variable names and same file names, so I don't confuse you. And no point in doing that. Let's actually look at the images. And there you go. And if you look at this and the other one, right? This image that you're seeing right now on the screen is where I have written my own for loop, to handle the patches. And here, it's Patchify. The result is identical. There's no reason, because I'm just extracting 256 by 256 patches and applying exactly the same trained model. So the result should be identical, obviously. And let's run the rest of the code, right, to do our measurements. And I'm curious if the measurements are identical. They should be. Yeah, that looks pretty much exactly the same, right? And also the final result. 77, 55, 49, 49, 74. Yeah, 77, 55, 49, 49. If I can find the previous one. Sorry about this. Let's see. Oh, there you go. 77, 55, 49, 49, 70. Yeah, identical. If you look at the area 4669, 4325, let's see if that's the same. 4669, 4325. It's almost like we are working on the same image, but no, definitely not. At least let me confirm that that's not the case, right? I mean, we are saving the result here as data results segment.jpg, and we are reading the same data results segment. When I see identical results, I get a bit worried because there's got to be some statistical deviation, but in this case, I don't see a reason why it should happen. Okay, so I hope you found this video to be useful. At least you learned 2 ways not to do semantic segmentation on large images. Always cut down your images into patches, and I showed you a couple of ways to handle patches. Now, the best way to actually deal with this without having the edge effects, because think of 256 and 256 at the edges. If you have a small an object just starting, but then it continued in the next frame, it will be fine in the next frame, but in this frame we may not have gotten good results right here. So it would be nice to actually have a sliding window type. For example, if I just do 128 right here instead of 256, this would be now 5 by 7, I guess. Let's run this, okay? I hate to extend the video, but this can be educational. So now you can see we have a lot more patches. Yeah, so the result is it's not bad actually. The result is pretty good even here. In fact, it's probably better than the other one, but I'm not sure. Let's see. No, it's almost identical actually. This is suspiciously identical to the last time results. Segment 1, image gray is image. I'm just checking if I made any, because the results look very identical, but they are slightly, let's see. Yeah, that's, I mean, as you can see, it's still, I mean, now I'll let you actually work with 64 size images, 64 by 64, and then see when you put together if you actually get similar results, if not identical results. Yeah, so again, I hope you found this tutorial to be useful, and subscribe to this channel so you get notified whenever I upload videos like this. Again, thanks again, and let's meet in the next tutorial, possibly extending our knowledge of UNet. Thank you.